Hey folks, here is a video detailing the Hardyweinberg equations and how to use them. It's designed to accompany 3 problems on the worksheet, and this will help you solve them. So we're going to start by just explaining what the Hardyweinberg equations are all about. Now, the 2 scientists who came up with this were studying allele frequency within a population. So they weren't looking at just 2 individuals getting together and passing on the alleles to their offspring. They're actually looking at alleles in a whole population of breeding individuals and working out how many of each allele there would be. So we're going to take a really simple scenario here to illustrate their findings. And we've got a scenario here, we've got lots of people, and we're just looking at one gene that has 2 alleles. It's either going to be a dominant one, capital A, or a recessive one, lowercase a. And this whole board here represents our population, and what the scientists who came up with the Hardyweinberg equation were thinking about was, well, let's look at the population, but actually we're not really interested in individual people. We're interested in the alleles and working out how many of each kind there are. So if you could go around the population and measure the alleles, or test the alleles present in each individual, you're not interested in the people, you just want the alleles. And you could count up how many of each kind there were. So to do that, you put them all together in a row like this, effectively, and tally up how many dominant alleles there are and how many recessive. And I have done this, and just by chance, because of the way I drew that population, we've actually got 12 capital A alleles and we've got 12 lowercase a alleles. Okay, so there was the 12 people on that page. Total number of alleles was 24, and it just so happens that they are in a 50-50 ratio. And that can be represented through some decimals. You can actually write out the proportion of alleles like this. Okay, so half of the alleles are dominant and half of them are recessive. Obviously in populations it can vary, and it's not always going to be 50-50. You may end up with a scenario where some alleles are significantly more common than others, and therefore they will be a much higher decimal, much closer to 1, and a very rare allele will have a decimal figure much closer to 0. So it's possible to have any value between 0 and 1 as the proportion of alleles in the population. What Hardy and Weinberg did was they represented this through a really simple equation. This is the first Hardy-Weinberg equation here. P plus Q equals 1. Where did the P plus Q come from, I hear you ask? Well, they realised their equation had to work for every single allele that you want to look at. And we don't represent every allele with a capital A and lowercase a or B's and C's. In fact, we use loads and loads of different letters. So they just chose a notation that can be applied to any system with 2 alleles. And they said, P, that, right there, that's going to be the dominant allele. And Q, that's going to be the recessive. But if you are looking at the proportions of these 2 and you add them together, if there are only 2 alleles in existence, then those 2 proportions will always add up to 1. And that's the first equation. It sounds simple, but it does enable us to do some useful things. For example, if you know the proportion of one allele in the population, you can very easily work out the other one. Now, Hardy and Weinberg went one step further than this. And they realised that in a population where everybody is breeding randomly, and there's an equal chance of anybody mating and passing on those alleles, and no alleles are favoured over the others, and you haven't got any mutation occurring, or indeed immigration or emigration of people. So you just have a stable gene pool with random mixing and recombining of these alleles. They realised that you're going to get alleles being passed on to the next generation. And they actually used that idea to come up with a second equation. What they did was they said, well, let's just imagine that we have 2 heterozygotes and they're going to breed. What are the possible genotypes of individuals? So we're no longer just thinking about the alleles in the gene pool. We're now thinking about the genotypes when 2 alleles are combined into an individual. So let's have a look. You could get P, well, actually, they wrote that as P squared. You could have P, Q. You could have another P, Q. We could have Q cubed, which again they wrote as Q squared. What they realised is that these are the possible genotypes, all of them. There are no other ways of combining these alleles. So, That means that if you know the proportion of a genotype in the population, you can actually add all those up. So they said, look, if we know the proportion of people who are homozygous dominant, and we add it to the proportion of people who are heterozygous, which is PQ, but remember, there's two ways of being PQ, so that's actually 2PQ, and we add the homozygous recessives, well, that's got to equal 1, because those are all of the possible genotypes in the entire population. So this is our second Hardyweinberg equation. This means that if you know the proportion of alleles in the population, you can often work out the proportion of each genotype of the individuals in the population. So just by knowing how common an allele is, you can figure out how many heterozygotes there should be, how many homozygote dominants, how many homozygote recessives there should be. Let's have a little look at a problem to work out how we would solve questions using these two equations. We're going to jot the equations at the top. Okay, we're going to use both of these typically to solve a genetics problem or solve a Hardyweinberg calculation here. So this is question 1 on the worksheet, and this is based on real data. And we're looking at cystic fibrosis in the US, and they tell us that 1 in 1,700 US Caucasians have cystic fibrosis. And the normal allele is dominant over the lowercase, the recessive one. Okay, so let's have a think about this. This is going to be P, this lowercase c, that's going to be Q. And we know that 1 in 1,700 have the disease. Now, in order to get the disease, you need 2 of those. Okay, so they are effectively Q squared in our notation. And we know that it's only 1 in 1,700 who have that genotype. Nobody else will be in this category. You can only have the disease if you have that genotype, and therefore you are Q squared. So that's our 1 in 1,700. Okay. It says, what percentage of the above population have cystic fibrosis? So they want CC or Q squared. Well, we've said it's 1 in 1,700, and if you calculate that, that's 0.0005888, which of course is going to equal, as a percentage, 0, because you just times it by 100 to get the percentage. That's going to equal 0.0588. So 0.0588% of the population will have cystic fibrosis. But as a proportion of the population who have it, that's this one right here. Okay, so we've answered A. From the above numbers, you should be able to calculate the expected frequencies of all the following, assuming a Hardyweinberg equilibrium. Right, calculate Q. Well, hang on. Remember I said that Q squared is the proportion of homozygous recessive individuals, and we found Q squared. Well, in order to get Q, you actually just take the square root of this. So we knew Q squared, take the square root of that and you will have Q. So Q, once you do that in your calculator, is 0.0243. This is the frequency of the cystic fibrosis allele in the population. Okay, 0.0243. So we've done that. Now we've got to calculate P from that. So far we've used this equation up here, and by solving for Q squared, we've got that. But now we can use this equation here, because P plus Q should equal 1. So what do I need to add to this to get 1? Okay, so we just do 1 minus 0.0243. Just make that look like a 0. Okay. And you'll get P, which is equal to 0.976. Let's go with 976. Very good at rounding there. Okay. So we've now been able to calculate P. We've got the frequency of the 2 alleles. For part C here, it's saying find the genotype frequencies for homozygous dominant and heterozygous. So let's have a think. Homozygous dominant, that's P squared, or in this example, big C, okay? And heterozygous, that's going to be big C, little c, but in this example it's going to be the 2pq. Okay, so those are the heterozygous. So we've got to find those. And the good news is that actually the maths of this is not hard at all. We've got P and we've got Q. Those are the only bits of information we need to do this. So I'm just going to get rid of everything else here and keep those bits of information. Okay. So we have P and we have Q. Right, so I need to find P squared first of all. Well, that's nice and easy. Take this number, times it by itself. P squared is equal to 0.952, 3 decimal places, if you square this number here. And then we have to find the heterozygous, the 2pq, so you would do 2 times p times q, which is equal to 2 times 0.0243 times 0.976, and you get this answer here, 0.0474. So these are the heterozygous. This is 2pq. Okay. Now, this is giving us the proportions of individuals in the population that follow these genotypes. Let's have a look at the next question. How many of the 1,700 individuals they talk about at the start, how many of those 1,700 are homozygous normal? Well, that's P squared, isn't it? Now, we've got a proportion, 0.952. If you times that by the 1,700, that will give you the number of individuals that are going to be homozygous normal. And if you do that maths, it comes out as 1,618.57. If you wanted to round that to a whole individual, I would guess you'd say you'd go up to 1,619. Okay, so we've only been able to answer that one there. Now it says in the last bit, it has been found that a carrier, so that's one of the heterozygous, they are better able to survive diseases with severe diarrhea. What would happen to the frequency of the C allele if there was an epidemic of cholera or other type of diarrhea-producing disease? So if you think about it, what's going to happen here is people without that allele are more likely to die. They will take their alleles with them out of the gene pool, and as a result, the frequency of C is going to increase. Because in that instance, it gives a selective advantage. Okay, now that's a Hardyweinberg example using real numbers from the real world. There are a couple of other examples on the worksheet. Have a go at those. Rewatch the video to follow the working if at any stage you get stuck. But I think it's relatively straightforward.